Test probes as the hidden backbone of industrial testing. This Pacta Industry episode is an industrial press-style review. The goal is to explain, in clear terms, why test probes matter, how the main probe families differ, and what those choices change in real production: quality, yield, troubleshooting time, and delivery pressure. Why a small pin has a big impact. A test probe is an electromechanical contact that temporarily connects a test fixture to a product under test. In practice, it is the difference between stable measurements that can be trusted at scale and intermittent contact that triggers false failures, retest loops, and long debugging sessions. As electronics become denser and production cycles faster, the probe is no longer a minor detail. It becomes a reliability lever. Consistent contact protects throughput, reduces rework, and helps teams meet delivery targets. Probe families and what each one is designed to solve. ICT, FCT probes. In circuit test, functional test probes are the workhorses of PCB testing used on loaded or bare boards. They are selected to match pitch constraints, pad geometry, required compliance, travel, and expected mechanical life. In high-density designs, the probe must keep repeatable contact even when centers get tighter and tolerances become less forgiving. Step probes. Step probes are built around precisely controlled travel and a step-shaped tip geometry. They are often chosen when repeatable compression depth matters, helping maintain consistent contact conditions across boards, fixtures, and operators. Switch probes. Switch probes add another layer, a controlled switch point that can be tuned to the application. This design is used when contact made needs to be verified as part of the test logic, supporting long life and dependable performance in repetitive cycles. Battery probes and battery interface probes. Battery-related testing and docking applications frequently rely on battery probes and battery interface probe (BIP) concepts, designed around package variability and repeated engagement. These solutions are often associated with demanding environments: medical, defense, rugged industrial, where reliability under vibration, shock, and repeated cycles is a requirement, not a bonus. High current probes. When current increases, probe design changes completely. High current probes are engineered to keep low and stable internal resistance, because any resistance becomes heat as current rises. Typical board test currents may be satisfied with lower ratings, but higher current functional test, wire harnesses, burn-in, or industrial power checks can require far more robust designs. A common strategy is to optimize base materials, plating, spring behavior, and tip geometry for current handling. Another approach is a feed-through plunger style, where reducing internal interfaces helps minimize resistance, useful when heat management and measurement stability are priorities.